Okay, good morning, students. So last time we have started with the when states are said to be in a discrete time Markov chain, when states are said to be transient and recurrent. So let us just continue that. So probability of first visit to state I in transition is recurrence time probability. If we sum those, we will get the probability of ever visiting state I, Fi. So if Fi is 1, that is return to state I is certain, then state I is said to be recurrent. If this is less than 1, then state is said to be transient state. And we have found the equivalent condition for that. And some examples we have given. So now we have last time shown that if states are communicating, then if one is recurrent, other is recurrent, that we have shown. Now let us show that if one is transient, other is also transient. So now I is transient, state I is transient, I and J communicate, then state J is also transient. So on contrary, suppose that J is recurrent. Since I and J communicate, this implies that Ij is recurrent and I and J communicate. This implies that I is recurrent, but it is given that I is transient. So this is a contradiction. So this contradiction will not happen if this is using property 1. This contradiction will not happen if J was your transient. So therefore J is transient state. In a finite state Markov chain, all states cannot be, whether my screen is visible to you, cannot be transient.
Yes, sir.
Okay. So in a finite state Markov chain, all states cannot be transient. So on the contrary, you assume that all states are transient. Okay. If all states are transient, then because transient state is visited finite number of times. Okay, so therefore, because all states are transient, so therefore some time will come when no state will be visited, because all are transient. Transient state is visited finite times. So therefore a time will come when no state will be visited, but that is not possible because process should be somewhere, discrete time Markov chain should be somewhere. So therefore at least one state should be recurrent. So therefore in a finite state Markov chain, all states cannot be transient. So this is for finite state Markov chain, in which states are finite. In a finite state irreducible Markov chain, all states are recurrent. So this is also clear because in the from P3, in a finite state Markov chain, all states cannot be transient. So that means at least one state is recurrent. Now using P1, because it is irreducible Markov chain, all states are communicating. If one state is recurrent, all other states are also recurrent. So using P3 and P1. Result holds because in a finite state Markov chain, all states cannot be transient. So therefore at least one state is recurrent. But this Markov chain is irreducible. All states are communicating. If one state is recurrent, other states are also recurrent. We're using P1 because all states are communicating with each other. In irreducible Markov chain, all states are recurrent or transient. So now irreducible Markov chain, because all states are communicating. If one state is recurrent, all other states are recurrent. If one state is transient, all other states are transient. But if it becomes finite state also, then all states are recurrent. But for infinite, it may be all states may be recurrent or all states may be transient, because it is irreducible. All states are communicating with each other. So consider a Xn to be a discrete time Markov chain with state space 1, 2, 3, 4 and 0, 0, 1, 0, 0, 0, 1. This is the TPM. 0, 1, 0, 0, 1 by 4, 1 by 8, 1 by 8, 1 by 2. So classify the states. So 1, 2, 3, 4. From 1 to 3 we can go. Then 2 to 4 we can go. 3 to 2 we can go. 4 to 1. 4 to 2. 4 to 3. 4 to 4. Okay. So you can see that state 1, from 1 to 3 we can go, then 3 to 2 we can come back. So from state 1 to 2 we can go. From 2 to 1 we can come back. From 2 to 4 we can go, then 4 to 1 we can come back. So 1 and 2 are communicating. Now 2 and 3. From 3 to 2 we can come back. From 3 to 2 we can go. Then 2 to 4 we can go. Then 4 to 3 we can go. 2 and 3 are communicating. Now from 4 to 3 we can go. Then 3 to 2, then 2 to 4. That means 1 to 2 T2. Therefore, this is one class. Equivalence class is only one class, 1, 2, 3, 4. Now this is all states are communicating, therefore irreducible Markov chain. Now, since this is finite state, irreducible, all states are recurrent. Finite state, in a finite state irreducible Markov chain, all states are recurrent. Okay. Now, also you can calculate whether Markov chain is positive recurrent or not. So first of all, M4, let us say that M4, we want to find M4. Okay, so that will be summation n F4 n. So now F41, that means return to state, starting with state 4, we are returning to state 4 in one step. In between, we cannot visit state 4. So this you can note down that this is 1, this is 1 by 8, this is 1 by 2. This you can just see from the, then 1, 1 by 8, 1 by 4. So you can write down simultaneously from the diagram, from the this TPM. Okay, now F41, that means this is 1 by 2. F42, in two steps we want to return to state 4. In between we cannot visit state 4. So we can go from 4 to 2, then 4 to 2, then we can come back from 2 to 1. That means 1 by 8 into 1. F43, F43 will be, we can go from 4 to 1, then 1 to 3. No. So in 3 steps we want to go. So 4 to 3, then 3 to 2, then 2 to 4. That is the only possible way if we don't want to visit in between state 4. So 1 by 8 into 1, from 4 to 3, then 3 to 2, then 2 to 1, 3 to 2 to 4. So 1 by 8 into 1 into 1. So F44 in 4 steps. So we can go from 4 to 1, then 1 to 3, 3 to 2, then 2 to 4. That means 1 by 4 into 1 into 1 into 1. That is the only possibility. In between, we don't want to visit some other state. And F45, yes, any case is there in which 5 steps we want to visit starting from state 4. In between, we cannot visit state 4.
So can you again tell the last one, 4 steps?
Yes, yes, yes. In 4 steps, you can go to 4 to 1, then 1 to 3, 3 to 2, then 2 to 4. 1 by 4 into 1 into 1 into 1. Is it okay?
Yes, sir.
In 5 steps, it is not possible in this case. So after that, all the probabilities are 0 because in between you cannot visit state 4. That is also the condition here. So therefore, mean recurrence time you want to find out. So M4 will be 1 into 1 by 2, 2 into 1 by 8, 3 into 1 by 8, 4 into 1 by 4, plus 0 plus 0 plus 0. So this is 17 by 8, which is finite. So therefore, state 4 is positive, recurrent, or non-null recurrent. So also all states are communicating with each other. So therefore, for irreducible Markov chain, all other states are positive recurrent because it is which are communicating, they are in same. Okay. So now let us start with the gambler's ruin problem. So what is a gambler? What is the problem here? The gambler has initial capital of rupees I. His aim is to achieve rupees n, where I is 0, 1, 2, and can take value this. So what he does, he plays a game in which he bets 1 rupee in each step. So Zi is the ith bet or step or transition or time, and each bet is independent. And in each bet, he gains 1 rupee with probability P, or he loses 1 rupee with probability Q. Okay. So what is the gambler's fortune after n steps? So Xn will be Z1 plus Z2 plus Zn. What will happen after n steps? Plus he has I rupees also. So this is the fortune of gambler after n steps. Now, if we can define Pij as probability x n plus 1 is equal to j, given xn is equal to I, where I and j belongs to state space, which is 1, 2, and which are the basically states here. Okay, so clearly here xn is a discrete time Markov chain because the process depends on the future will given the present and the past. depends on the present only. So
Sir,
therefore, yes.
sir, why is state space just limited to 1 to n? Sir, what if he gets more than n in some intermediate step?
No, no, he will not play the game then, because once
He will
his
stop.
aim is achieved, he will stop. Okay,
Okay.
because his aim is achieved, he will not play. When he will have 0 rupees, nobody will allow him to play because he doesn't have any money.
Okay.
Okay, so now so gambler till now we have done that. Gambler has initial capital of I rupees, where I can be 0, 1 to n. If he has 0 rupees, nobody will allow him to play the game. If he achieve his aim, he will not play. His aim is to achieve n rupees. So he plays a game in which in the ith bet he bets 1 rupees. If he gain 1 rupee with probability P, he loses 1 rupee with probability Q. And each bets are independent. Then what is the gambler's fortune after n steps? So that will be Z1 plus Z2 plus Zn plus I clearly. Also, Xn is a discrete time Markov chain because the future here depends on the given the present and the past depends on the present only. So Xn is a discrete time Markov chain. So now what will be P 0, 0? If he has initially 0 rupees, finally he will have 0 rupees with probability 1. If he have n rupees, finally he will have n rupee with probability 1 because he will not play after that. If he have I rupees, then he will have I plus 1 rupee with probability P because he will gain 1 rupee with probability P. If he has I rupees, he will lose 1 rupee with probability Q. I is from 1 to n minus 1. So Xn here is a discrete time Markov chain where n is 1, 2, so on. Okay. So now, so we can write the TPM here. So 0, 1, 2, n, 0, 1, 2, n. So if he have 0 rupees, he will have 0 rupee. Other probabilities are 0. Similarly, from 1 to 0, he can go with probability Q. From 1 to 2, we can go with probability 0. So 0 Q, 0 P, so on, 0, 0, 0, 1. Okay, so in this fashion, this is the TPM here. Now, which states are, let us say which states are recurrent, which states are transient. So let us draw the first of all the state transition diagram. So so 0, 1, 2, n minus 2, n minus 1, and so from 0 to 0, from 1 to 0 it can go with probability Q. From 1 to 2, 2 to 1, P Q. From n minus 1 to n, then it will remain in n with probability 1. Now, from it is clear from here that 1, 2, so on to n minus 1 because they are communicating with each other. They are in one class, 0 in separate class, n is in separate class. Is it clear? Because 1 and 2 are communicating, n minus 2 and n minus 1 are communicating. So all these are basically communicating with each other. So therefore, 1 to n minus 1 in one class, 0 is separate class, n is a separate class. So which states are transient, which states are recurrent? Because You can see here that the process will, if it is in state 1, let us say in state 1, then finally either it will go to state 0 or state n. Okay, so therefore it cannot stay in state 1 infinitely often. So therefore 1 is a transient state. So therefore if 1 is transient, so all of them which are in one class are transient. Okay, so this is a transient. Now 0, because if we are in 0, we can remain there in 0 for infinitely often, therefore 0 is a recurrent class. Similarly, recurrent also, it is absorbing also. If something is coming inside, it cannot go outside. So that is absorbing also. Similarly, recurrent, n is also recurrent, which means absorbing also. Okay, so this is the basically. Any question till now? Now, is any question till now? Okay, now let us say that T naught, let T naught is the time gambler broke. That means this is the minimum of infimum of n such that xn is equal to 0. The first time the gambler's fortune take him to 0. That means he doesn't have any money. Time he broke. Tn is the time he has rupees n. That means his aim is achieved. That means for first time, infimum of n such that xn is equal to n. Okay. Now we are interested in finding the probability that Tn is less than T naught. That means this is the probability that starting with rupees I, the gambler's fortune will reach n before reaching 0. So we want to find out this probability. How much is this probability? Let us say we are denoting this by Pi because he is starting, he has I rupees and gambler's fortune will take him to rupees n before he reach 0, because once he reach 0, he cannot come to have n rupees. Okay, so the probability that gamblers will, starting with I rupees, have n rupees. So Pi now using theorem of total probability, this is probability Tn less than T naught given Z1 is equal to 1, probability Z1 is equal to 1 plus probability Tn less than T naught given Z1 is equal to -1 into probability Z1 is equal to -1. using theorem of total probability. That means PI, this means that starting with I plus 1 rupees, gambler will achieve his aim. So that means this will be PI plus 1. And this probability is P. Z1 is equal to 1. Is P basically. Okay. So now plus this value will be, because he has I rupees, in one step he will lose I 1 rupee. So therefore P I minus 1 into Q. Okay. So this is the value. Okay. Now this can be written as PI plus Q, PI because P plus Q is 1, is equal to PI plus 1P plus PI minus 1Q. Now solving this basically. So this implies that PI plus 1 minus PI into P, these two values, is equal to Q PI minus PI minus 1. So therefore, this implies that PI plus 1 minus PI is equal to Q by P into PI minus PI minus 1. So when I is equal to 1, this implies that P2 minus P1, which is Q by P, P1 minus P naught. Now what P naught is basically, starting with 0 rupees, gamblers will have n rupees before he reach 0. What is that probability equal to?
0.
0. That is clearly 0 because he has 0 rupees. Nobody will allow him to play the game. Also, Pn is also 1. Also, you note down that Pn is also 1 because he has already n rupees. He will not play the game. So he will have basically n rupees, that P1. Okay, so therefore this is Q by P, P1. So now I is equal to 2, P3 minus P2. This is Q by 2. Now P2 minus P1, plugging in this equation itself. Now using this equation, this will be Q by P square P1, and similarly PI minus PI minus 1 will be Q by P raised to power I minus 1 P1. So solving this in this fashion, now adding these quantities, we will get Pi minus P1 because quantities are cancelling out. This will cancel. This will cancel like this. All these quantity will cancel out. So in this fashion, we will get this value as P1 Q by P plus Q by P square plus Q by P raised to power I minus 1. So this is the value. Now Pi will be P1 1 plus Q by P plus Q by P square, because this P1 I can take other side, Q by P raised to power I minus 1. So therefore Pi will be, if Q by P is not equal to 1, then this is clearly 1 minus Q by P raised to power I upon 1 minus Q by P into P1. If Q by P is equal to 1, then this is 1 plus 1 plus 1 plus 1 So I times, so therefore I times P1. Okay. So this is let us say equation 1. Also Pn is 1. So if we put I is equal to n in 1, so therefore we get 1 is equal to 1 minus q by p raised to power n. So from there we will get, because P1 is Pn is 1, so therefore we will get value of P1 from there. So P1 is equal to 1 minus q by p upon 1 minus q by p raised to power n, because this quantity will go other side with I is equal to n. If q by p is not equal to 1, and this will be P1 will be this I is n and Pn will be 1, so 1 by n. If q by p is equal to 1, so this is the value we are getting. If we put now plugging in this value using 2 in 1, so we will get Pi is equal to 1 minus this 1 minus q by p will cancel out. So 1 minus, so 1 minus q by p raised to power I, this quantity, and divide by this quantity. So divided by 1 minus q by p raised to power n. If q by p is not equal to 1, and this is P1 is 1 by n. If q is q by, so this is I by n if q by p is equal to 1. So this is I by n if q by p equal to 1. So this is the answer we are getting. So now q by p is equal to 1 means, but we know that this is q is 1 minus p. So this is 1 minus p is equal to p. That means this is equal to 2p. So that means p is equal to half. That means p is not equal to half. If p is equal to half, for example, if we are tossing a coin, if coin is fair or unbiased, then we will get I by n. If that is unfair, if that is not fair, then p is not equal to half, then we will get 1 minus q by p raised to power I upon 1 minus q by p raised to power n. So let us say that, so this is the answer we are getting in general. This is the probability that starting with I rupees, gambler will achieve his aim before getting broke. So let us suppose that we are playing against a casino, assuming that casino has large amount of money. Okay, then what will happen? If this happens, okay, then Pi starting with I rupees. Now, if P is equal to half, then this will be 0 from here. Now, if Q by P is greater than 1, then from here this will be 1 minus limit as n goes to infinity, 1 minus q by p raised to power I, 1 minus q by p raised to power n. So that will be n goes to infinity. So therefore, this is something divided by infinity, that will be 0. So therefore, if q by p is greater than equal to 1, that means p by p is less than equal to half. Okay, then this is 0. If we assume that q by p is less than 1, then from here, as n goes to infinity, this quantity 1 minus q by p raised to power n, as n goes to infinity, this is 1. So we will get 1 minus q by p raised to power I if q by p is less than 1, that means p is greater than half. So what we are saying is, if we are playing against a rich adversary or a casino which has large amount of money, then if we play a fair game or p is less than half, then our chances of getting our aim of n rupees is 0. If p is greater than half, then there is a chance that the probability is that 1 minus q by p raised to power I, that we will achieve our aim of having n rupees. Is any question till now? Okay, let us take some examples. Let this is assignment gambler student problem. Question 1. A rat is put into the linear maze as shown below. So in the compartment 0, if he comes, shock is there. Compartment 1, compartment 2, compartment 3, compartment 4, compartment 5, compartment 5, food is there. So let us say rat is here. Okay, so his aim is to, so at each step, the rat moves to the right with the probability 3 by 4 and to the left with the probability 1 by 4. What is the probability that rat finds the food before getting shocked? Okay, so now this is basically gambler student problem. So starting with 2 rupees, gamblers want to have 5 rupees with the probability of success as probability of getting to right side is 3 by 4. Okay. So, so what is the probability that rat will find out the food? So that will be P5 basically. So that will be 1 minus Q by P raised to power I upon 1 minus Q by P raised, but Q by P here is, Q is here 1 by 4 and P here is 3 by 4. So therefore 1 by 3. So therefore this is not equal to 1. So therefore this is Q by P raised to power uh, N. So 1 minus 1 by 3 square upon 1 minus 1 by 3 raised to power 5. So therefore this is 0.892. So this is the solution of this. So any question here?
So here, even after reaching 5, he can again go to uh, other states.
Yeah, but basically, yeah. So was because once he comes, so then he will finish the food basically. So after that, so basically we want to find that thing basically, that
So sir,
find the
here
probability that,
can we say that he will get the shock certainly? Like he will
yeah,
certainly
yeah,
get shock at
because
some step.
yeah. So that also you can find out because two sides are there. Either he will find, because you know that states here 1, 2, 3, 4 are transient, 0 and 5 are here recurrent states. Okay, so therefore either he will go to 0 or 5. So because only two states are there, so which are, so therefore other value will be 1 minus P5. That rat will get the shock, or either you can find out in same fashion. Okay, rat find shock get shocked before getting food. Okay, so this is 1 minus P5. So that is the answer. So let us take another example. Consider a discrete time Markov chain having TPM 012 012 and 100 0.4 0.6 001. So this is basically starting with 1, determine the probability that the Markov chain ends in state 0. So here also 0, 1, 2, and from 0 to 0 with probability 1, 1 to 0 with probability 0.4, and 1 to 2 with probability 0.6, and 2 to 2 with probability 1. So 0 and 2 are here absorbing or recurrent. Okay, so we can say 0, 1, 2, 0, and these two are basically absorbing, or we can say absorbing or recurrent. and one is basically transient state. Okay, so this is also we can solve by, so we want to determine starting with 1, determine the probability the Markov chain ends in 0. So this is also basically gambler's ruin problem. So this will be 1 minus, uh, here P is 0.6, Q is 0.4. So Q by P is 4 by 6. That means 2 by 3, which is not equal to 1. So 1 minus 2 by 3 raised to power I upon 1 minus 2 by 3 raised to power n, 2. So therefore this is required probability is equal to this value, which is 1 minus 1 by 3. Okay, 1 minus 1 by 3 upon 5 by 9. Okay, so therefore answer is 0.4. Okay, so this is the answer here. Okay, so let us stop here. So next time we will continue from here. We will some limiting probabilities we will start with. So any question till now?
Sir, can we so we want the probability of going from 1 to 0. So for our convenience, can we redefine the probability as 0.4, because we want the probability of going from 1 to 0. So P is equal to 0.4 and Q is equal to 0.6. Uh,
Yes,
sir,
yes, 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 yes. So yeah, so you can do that fashion also, because the same thing we are doing basically.
but then, sir, should we change n from 0 to 2? Because uh, we will also have
Yeah,
to
yeah,
change.
yeah, yeah, yeah. Then you have to basically interchange the quantities. That is the thing. Yeah.
Okay, sir.
So you can try that thing also. Otherwise, once we have done that, because two states, absorbing states are there in, then we can do in this fashion also.
Oh, so, sir, one more doubt from previous class. Hello?
Yes, 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 yes.
Sir, in a class, if uh, uh, so in a class, do all the states have equal di? Sir, the period.
Equal period, yes.
So how can we prove that in a class that all states have same period?
Yeah, so that proof is okay. I will, because time is not there. So next time, okay, I will write down that proof and just, yeah. So basically, you have to show that in some steps, if some state X and Y are there, so then you have to show, because in M steps you can go there, Y to X. Okay, I will just write down that proof. Okay, so that will actually take some time. So okay, I will do that thing and give you the proof of that.
Okay, sir.